So far, our traffic game had very intuitive results. If players all congest the same pass, that slows them down. And that's not a Nash equilibrium of the rating or traffic game, as they all prefer to go on the faster alternative route. The Nash equilibrium is if they split the traffic evenly. And doing this, they improve the travel time from 105 minutes to 80 minutes, which is better for everyone. However, results can get very intuitive really fast. Today, we're going to think about what the effect is of adding an extra edge. One would think that adding an extra edge should help. Extra edge gives an extra option or some way they can drive. It doesn't force anyone to take the pass, so they can spread out more, and more options hopefully gives them better travel time. But it turns out that this can actually hurt. This was discovered by a German mathematician called Braess, and the example that shows this is called the Braess paradox. So Braess paradox starts with the very same example we have seen in the last segment, the same game with, say, 500 travelers going from a node A to another node B with two options, either going through C or through D, and each of these segments have these travel times where AC and DB are very congestible, and the travel time is increasing with the amount of traffic. The extra edge we want to consider is an edge from C to D, and to make the example extreme, I added an edge that takes 0 minutes, an extremely fast highway with a 0-minute instant connections from C to D. So now we want to think about what happens to our 500 travelers and what happens to the Nash equilibrium if we add this extra option, a super fast road from C to D. To start with, we can think about what the previous equilibrium will feel like. So previous solution was 250 people in each of the two options, and they took 80 minutes, like 25 minutes on the congestible part and 55 minutes on the fixed time highway for a total of 80 minutes. Unfortunately, this is no longer a Nash equilibrium. It still only takes 80 minutes, but people now think they have better options. And in particular, every single one of the travelers would prefer the interesting alternate route on which they drive from A to C to D to B, that is, going through both of the congestible edges simultaneously. If they do this, remember X was 250 and Y was 250, so they're going to take 25 minutes on one edge, 0 in the middle, and 25 minutes on the next edge for a total of 50 minutes, which is a lot better than 80 minutes. And indeed, this shows that the solution is no longer Nash equilibrium. People prefer this A to C to D to B pass. So what is a Nash equilibrium? It turns out what's a Nash equilibrium here is simply everyone to follow this alternative, this path that at the moment seems much, much shorter, taking 50 minutes instead of 80. If everyone follows it, however, life gets worse. So what does it look like when everyone follows it? So all 500 travelers go from A to C to D to B. X and Y both become 500. And the travel times on these edges is X over 10 and Y over 10. Both are 500 over 10 equals 50 minutes, for a total travel time of 100 minutes. 50 minutes on the first edge, 0 in the middle, and another 50 minutes at the end, for a total travel time of 100 minutes. So definitely life got worse. In this solution, the total travel time went from the previous 80 minutes now to 100 minutes. But we're going to claim that despite of this, this is a Nash equilibrium. To see this, we have to see whether people have alternatives and what they can do. So what's an alternative is a different strategy that one of these travelers could follow. So a traveler could, for example, think that while everyone's following this three-hop path, he or she will go back to the solution that worked better for them last time and go from A directly to D and then to B, for example, or similarly could do this to denote C instead of B. So going through D, it's shortcutting the A to C to D to edge and doing the direct pass from A to D. Unfortunately, that direct pass takes 55 minutes, while the detour, following the X edge, A to C to then to B, only takes 50 minutes. So this is not a good strategy to respond, and in fact, the best strategy for every player is to stay on the path they're following, every one of them following this bad A to C to D to B pass. And remember, the traffic time went from 80 minutes to 100 minutes. So what we have seen here is that adding an edge can hurt the Nash equilibrium. Without the edge, the travel time in Nash equilibrium was only 80 minutes, but with the edge added, the travel time went up to 100 minutes. Thinking about travel and travel planning and route planning, this does seem very paradoxical and sounds surprising, but if you think about it in game theoretic terms, actually it's much less surprising. We, in fact, have seen a game with this property. Our very first game, the Prisoner Dilemma, also can be thought about it this way. So Prisoner Dilemma had two strategies, to confess or not to confess. I can think of an even simpler or maybe more basic game, which is maybe not even a game really, a Prisoner Dilemma where I only allow people one strategy to not confess. If neither of the player confesses, then they both get this very short prison sentence because, remember, the police can't prove their crimes without the help of the other prisoner. So this game, with everyone having a single strategy not to confess, has a unique equilibrium, in fact, has a unique outcome because they had one strategy, and that's pretty good for both players. If now we add an extra strategy, we now suddenly allow them to confess. We add an extra strategy to the player, to the game. Then we have seen the unique Nash equilibrium for them both to use this extra strategy, and as a result, both have long prison sentences, as the police now has enough evidence to convict both of them. So Prisoner Dilemma shares the property with Braess paradox that adding a new strategy to a game can indeed make the outcome worse for everyone.